Okay, the other thing you'll remember is that on our Wednesday classes, they're exactly 1 hour. We'll stop 5, 10 minutes sooner than we would have because I have to transition and they don't give me enough time to kind of get from one to the other. So I split the difference with them. Okay, so here is where we were at. We were going through cable access networks and we'd finished going through DSL. And we're talking about how you get the traffic from your computer at home onto the internet. It's usually the slowest link. So what kinds of things might you see that we've done as designers to put more bandwidth in your hands, and what implication does that have for us as people trying to use and design networks as computer scientists? So the cable network was inherently broadband. It was inherently a very wide bandwidth. It can handle lots of frequencies, and so you divide them up and put a television channel on each one of them, just like you would put a different radio station on each number on your radio dial, and that block of frequencies can be carried by the airwaves. Well, if you took that block and put them on a cable, some cables can carry just as wide a range of that. So that's kind of what we've done. And then we just robbed some back, took them away from video, and made them data instead. So that's what you see happening. They collect this data from their subscribers. They get it at a central location, an office where they have a cable converter that they'll call the cable head-end system. And university may have something like this in some of the older dorms, for example. And then from there, it gets dumped onto an ISP, just like anything else. And like DSL, it's also typically asymmetric in that you can have lots of speed down, but you don't need much up. So it's not a choice if you're trying to run a business and you have a server and you're trying to push content. You'd be better off maybe saving the money from buying a really expensive communications link to solve that problem, and instead keeping the money and renting and pushing that content into the cloud and letting somebody else serve it up for you. So there's a whole variety of these technologies out there, but basically all we're doing is connecting these things up. And then from a home network, you're usually going to just have one integrated device. This sort of breaks it out as three. Cable, modem, router, or firewall. It may have NAT running. It almost certainly will. You'll very often have the same network number, private 192.168 that everybody uses, and you'll have Wi-Fi built into it as well. But in the book, they kind of break it out into three devices, so you have a little better idea of kind of what's going on. And you can sometimes get good network connectivity among devices at home, enough to connect devices together. Not all of your traffic, after all, has to leave the network. Some of your traffic is going to the printer. There's home entertainment systems that'll redistribute content. AT&T redistributes their content now, sometimes over Wi-Fi from your master receiver to some of the subordinate ones, and they kind of set up their own little network to do that. So it's becoming a way of getting almost anything done that requires communications in the house. For larger organizations, for enterprises, they design things differently. They'll have some switches and they'll have a router for sure at the edge of the network where they'll purchase a higher capacity, usually fully bidirectional, evenly, symmetrically bidirectional link to carry traffic down and up, because they almost always have servers. So typical in Houston, we'll have a gigabit per second connection that goes over to Baylor College of Medicine, to that area, and then maybe a backup one that goes to AT&T or somebody like that. We don't use AT&T on campus. There's also wireless networks. They fall into two categories: wireless LANs and then wireless WANs, which we'll just call wide area. The WANs are where your cell phones exist, and also where some other enterprise networks exist that send things between two specific points. Wireless LANs, on the other hand, are almost all Wi-Fi. There are some other technologies as well, but just as I showed you on that big map, usually what the government's trying to do is auction something off for money and prevent anyone else from using it to give it exclusively to someone. Sometimes they do exactly the opposite. They prevent anyone from using it exclusively or using it with high power that would interfere significantly with others, and they refuse to take money for it. It's donated to the public domain, so no one needs a license. And that's what Wi-Fi is. So just remember with Wi-Fi, because it's not restricted, at any point somebody else can bring a Wi-Fi hotspot into the classroom where you're trying to use the one from U of H and can compete with the radio frequencies that that one's trying to use, and it may interfere with your ability to transmit. In fact, I would suggest to you, since almost everyone has a phone with a Wi-Fi hotspot built in, you guys are doing that right now, and yet somehow it still manages to work. It's pretty resilient. All right, so how do we get data across? We're going to take information and send it as packets. For information before we needed to send packets, we sent things as a continuous, endless stream of data. Initially as an analog signal, because initially all we really had to do is take a sinusoidal signal and decide how we want to perturb it to make it interpreted as ones and zeros. And that's overly complicated. I could do something simple, like make that mean a 1, and if it's a low voltage, 0. Or I could just even say, you know, if it's above the line, it's a 1. If it's below the line, it's a 0. And that would imply that you have sometimes signals that look like this. And you do. You can invert phase, and you'll have some signal, some transmission technologies that use a pattern like this. So let's take this one specifically as an example. In the old days, you had ones and zeros to send. Maybe you sent them as letters of an alphabet or something, or you said them. Let's say you speak them out loud. Speaking them out loud might generate a signal that looks like this, but because it's very noisy on the line, by the time it arrives at the other side, it looks more like this. And you'll hear the difference. You'll hear the noise. So if I make an international phone call to the WebEx bridge in Richardson, Texas right now from my phone sitting in Mexico next to me here, you'll definitely hear a difference in the quality between, you know, from this that I've got. And some of what you'll hear is noise. You'll hear background humming and maybe hissing sounds, and so things creep into the signal. So one big driver for moving from analog to digital was to make us far more immune to those problems. And here's how that would work. If I told you this was an analog signal, there's no way for you to return it from the red path back to the gray path easily. It's sort of, how would you know what it's supposed to be? But what if I told you that what I was really trying to transmit was up here, and what showed up at the other side looked like this, all this noise on there? Could you still pick out the ones and zeros out of this? I mean, are you still able to tell that this was probably a 1, and yeah, this is all over the place, but it's lasts 3 clock cycles long, so that must have been 3 zeros. And this one is 100% above the line, and it finally gets its way above my nervousness threshold. So we can call this one a 1, and the same thing here. And this one's a really hard call. I might throw out this packet, or I might at the last minute decide to call it a 0 and, you know, maybe a 1. So I drew this intentionally badly, but what I wanted to show you was you have a much greater likelihood of being able to pick the signal out from all the noise, even if the signal is perturbed, you know, dramatically. I could even take a signal like this and do something like, and just if it's short enough, you'll still ignore it. You can have grave errors that would have hurt people's ears if what you were doing was sending the signal analogically. So that's the motivation behind sending everything as ones and zeros. So back to packets. We had ones and zeros long before we had packets. What we would do is use an encoding scheme like this to send voice calls, but it was an endless, continuous stream of data between one point and another. And so if it was a phone over here and another phone someplace else, we would configure our gear, our telephone switches in between, to give you the belief that this was one continuous wire, even if it went from Houston to Mexico City through, you could probably believe, hundreds of devices. I mean, intuitively, you know there have got to be lots of devices there, but yet there's nothing to suggest to you that it's a packet because there isn't. They just let the bits, that sine wave flow through. Occasionally something may pick it up and throw out the noise and regenerate it fresh again, and then it's just exactly like the original. So if you take a photocopy of a photocopy of a photocopy of a photocopy, it looks bad. That's what you're doing down here in the analog world. But if you take an MP3 file and you make a copy of it and another copy of that one and then a copy of that one and a copy of that one, it's still the original data, exactly the same string of bits. So that's the difference between using digital to encode information on an analog signal versus just letting it ride analogically to begin with. It's still riding on analog at the bottom. It's still a point-to-point circuit. So what do we do now if we want to come up with a scheme where we need to share one of these expensive communication links with other people? So the idea is you're going to have a router between here and here. And if you remember kind of the ARPANET story, you've got some people in California and some people in the Boston area. And this circuit is super expensive. So this person is not going to buy one to talk to this one, and this one's not going to buy one to talk to this one as well. If they're next to each other, they're going to get together and go, is there not a way for us to share this? Because these, relatively speaking, are cheap. These are sold by the local telephone company, Pacific Bell. It would have been called Pactalesis or something like that. And I don't think it was California Bell even a ways back. And this would have been New England Telephone or something like that. And this is sold by like an AT&T. And it would be super expensive. So if you're going to share this, now you just can't sort of combine your ones and zeros and let them flow. How would you tell them apart? So we put this idea together, Paul Barron did, of grouping these things together. 10011. You fill this thing up with just your packets, and we'll put something at the beginning, some special pattern of bits so that we recognize it as the beginning of a packet, and we'll do something else maybe at the end, and we'll send it across this shared wire. We're also going to have to put some information in to say who's it supposed to go to when it gets there. And this scheme, if we follow it, will allow us to share this link with a bunch of users. Now, what does the phone company think's going on? Nothing different than has ever gone on for the last 150 years. There's a sine wave, you're perturbing it, they're using some encoding, and in the digital age since the 70s, which is 50 years still, 40 maybe, then they're still going to see this as the same. The fact that you're sharing and sending one person's ones and zeros and then someone else's actually was a court case. You are creating a little telephone company over this wire. You're letting 4 different people use this circuit. And normally, I should be charging each of them for using a circuit, and they should be buying a circuit for me. So we tried getting money that way, and all this stuff got settled in the right way by the FCC, and it's set law, and it's the way everybody pretty much does it. So that could have killed the internet, early on. There are a lot of barriers. The thing that you see now that's the internet, there may have been 100 things like it, ideas that fell by the wayside because of money, politics, and religion up at the top. So now we have a way of sharing this stuff, and we're going to have packets, and we're going to continue to use that packet idea even when it's only us at home using this DSL or cable modem link. We've got the software. It knows how to do packets. We're comfortable with that. Let's just stick with packets. We don't need to revert back. Let's everybody do packets. And if you tell me how big the packet is, and you tell me how many bits a second I can encode on the wire, I can tell you how long it's going to take from the time you say go to the time that entire packet makes it onto the wire. Now the first bit is long gone. He's long raced ahead, and he's at the other end of the network maybe. Maybe he's still in the middle somewhere, but you are busy still stuffing bits in as fast as you can. So think about this like a toll road where the gate opens and you let the first car go. That's a packet. The nose of the car enters the road first. It takes time for the whole car to clear the gate and for it to come back down again so you can be waited on. That's the transmission time. Once the car is on the road, how long it takes the car to get to the other end, to the next toll booth, that's the propagation time, the transmission, the propagation speed, close to the speed of light, don't we wish. So this formula is only dealing with the transmission delay. It does not deal with how long it takes the bits once they're on the wire to make their way to the other end. Okay, so there's a simulator for this. in the book's information, and it's called a transmission versus propagation delay. And so what I'm basically going to show you here is a length of cable, a certain speed, transmission speed, and a packet size. And what it's going to visually show you is that at this moment, the cable is completely occupied just sending your bits. They're one at a time in single file, but not for 1.6 milliseconds approximately will the network become available for someone else to use it. And I say approximately because they're counting the time it takes to enter at the other end, which they shouldn't. There's, I think, a bug in the algorithm that they're using here. So that sort of showed, if I do it again, the first packet starts to fly across, and it has already made it at the receiver, and you are still sending at this end. All right, and if I, as you may have seen, if I increase the size of the network, it takes longer for it to get across, but this packet's still big enough to occupy the entire network at a time. What if I speed up the network? And remember, it's not speeding up how long it takes to get across the wire. It's speeding up how quickly I can encode a 1 or a 0 in a sine wave. And so what I want to do is dramatically increase that, double it, and let's see what it looks like now. So I will, it's going to be a little bit better, but still fills the whole thing. Let's make it even faster, 10 times faster, and see what it looks like. So now the whole packet is on the wire. The very last bit was not very far behind the first bit, now that I've increased the rate at which the network can absorb the bits. And so now there's space immediately behind it much sooner to send another packet. So increasing the transmission speed really does get you finished sending your packet and let you move on to the next one, which lets you send the next one sooner and the next one sooner. And so it speeds your network up. So that's why people say it's how fast is your network. In fact, if I make the network really, really long and I make the transmission rate really, really fast, then you can get these silly kind of things here where there's just like one little red bar working its way across the network and one little red sliver. So if this is all you used your system for, you would get yelled at by your boss because you're leaving the network heavily underutilized. So you'll have a homework problem that's going to ask you to do a couple of these things, but then I'm going to ask you to calculate something on your own, and I'm going to ask you basically, is the simulator correct or are you? And you're going to have some confidence on your answer because they're going to be different. I can tell you I believe they'll be different. Okay, so back to the slides. We've got the ability to send the data along. So if you tell me what kind of media you're using, I can start writing in some of these numbers. So bits propagate over some type of physical link. If it's physical media as opposed to wireless, it might be copper, might be fiber, but in things that are cables, we call it guided media. And among a whole bunch of other things, one of the big implications of this is all of the energy that you impart into your oscillation stays conserved inside the cable. It doesn't leak out and broadcast everywhere at once like wireless does, which dramatically weakens the strength of your signal immediately. With cable, you can go lots further, sometimes many, many kilometers, and still have a decipherable signal at the other end. Unguided media are where things propagate just freely, like throwing a rock in the middle of the pond. The energy you created from that goes out in waves, but it goes out all in a big random area. Whereas on the other hand, if you threw the rock into a canal, and there'd be much more of the energy preserved that would come in one direction, and you might notice it more. Types of media include things like twisted pair copper. These usually unshielded twisted pair. UTP is typically what you'll see printed on some of these things. And these names that you see, Cat5, Cat6, refer to the IEEE standard that governs exactly how the cable is to be manufactured and installed and managed. Other types of cable include things that the cable company use, like coaxial cable or hybrid fiber coax cable, and pure fiber optic, which is basically glass. And they add chemicals to the glass to improve its ability to carry light for a great distance. Why do we use fiber? Because it's immune to the types of radio range electromagnetic spectrum problems, and because you don't you don't see those. Those don't show up as light waves, so it's immune from that kind of stuff. The problem with doing this is that the colors of the light tend to drift as they go through a long distance of glass, and it's expensive to make lasers that emit a pure single frequency wavelength of light, a certain color, if you will. So if you're going to build a fiber, one of the nice things that keeps improving about fiber that you've got in the ground is, see if I can draw this a little straighter for you guys here. In fact, I'm going to use a different color as well because this is going to mess up my example if I don't. So here's my fiber, and I'm going to make it go in kind of a roundabout way. Kill a bunch of birds here with one stone. And let's say you want to send ones and zeros over it, and this is your pattern. So you're going to have a little laser that emits a color red, and you aim it into the end of the fiber, and it will make its way through. And if the fiber is polished properly and it's not bent too much, then it'll bounce off the walls as opposed to hitting a spot where maybe it's rough and not smooth and the light gets absorbed and some of the energy leaks out. You want to avoid that if you can, so you protect this with very often you'll see kind of this woven fiberglass baby diaper, smooth, soft little cloth sheath around the fiber so it doesn't rub up against, anything. And the light comes out at the end, and you just have a receiver that receives this color, and you turn it back into the signal. Okay, and we can make a laser emit another color and double our bandwidth. Double the bandwidth. Who wouldn't want that? So this thing will make its way through as well and come out. But here's where things sort of become complicated. And I'll draw one more here. In fact, we're good at doing dozens of colors with dozens of different lasers, and they all go into the same fiber, but the colors combine. That's the problem. So just like all of the frequencies combine from all of the things emitting colors, reflecting colors, bouncing off of colors, and you think are white, like coming in through your window, for example, well, if you took a spectrograph of it, you'd find lots of different wavelengths of light combining together. Our brain just tells us, let's just call that white. And same thing happens inside a fiber. The colors that come out aren't individual. It's a single combined wavelength that has all of these different colors in it. So what you have to do is you take your hybrid signal that's coming out, and let's say it's, I don't want to use that tool. Let's use this one. Your signal's coming out, and it's got a whole bunch of colors built into it. So what you're going to have to do is build yourself a mirror, but it's a partially reflecting mirror, and it lets part of the signal go one direction and part of the signal go another. So part of your signal will continue on, this way, and part of it will move up. And maybe you want to make it 50-50. So half of the strength of the signal gets sent one way, and you'll put a filter here that absorbs all the colors of light except for red, and only red passes through, and now you can reproduce this situation down here. And the other half maybe goes to a different reflector that absorbs all the colors of the spectrum except for blue, and only blue passes through, and you can put a receiver there and get whatever they were sending. So you may have to split your signal 30 times. So that's going to limit how far you can go because you're cutting the signal to 1/32 its strength for every receiver. So you need really good sensitive receivers. You need really good mirrors. You need very accurate ways of building it. And you need people to still get a signal that's strong enough. So you may end up having to go much less distance and before you have to regenerate the signal. But it's if you can figure out how to add another laser and get it to work, you've just added more bandwidth without ever having to touch anything in the fiber. You also can have radio that carries things around. Radio has some other really hairy problems because they have propagation issues. So propagation issues are copies of signals that make their way from your source to your destination. And the best way to demonstrate this is to try to draw you a little animation or a little diagram here. So let's say I'm standing at one end of Westheimer near the Galleria, where there's a bunch of tall shops and buildings on both sides of the street. And you've got a variety of things here. And these are your usual downtown kinds of buildings. They've got lots of glass and stuff like that. And down at the end, sitting on top of a building, you can see a cell tower. And the cell tower's got some antennas on it that are just waiting to receive a signal from you, and they're sending signals back. So here you are. You can see it. It's maybe half a kilometer away, and you've got your phone in your hand, your fancy new iPhone 10, and you are sending out a signal. And you are talking to someone, and you want the signal to reach the other end, or you're sending out a packet to ask for a web page. You need the signal to go from here to here, but that's not what it's going to do because it's a radio, and the signal emanates in all directions at once. So if I just draw it as a 2D problem, what's going to happen is the signal is going to propagate out more and more widely, and I'm going to start drawing these as kind of a sphere here. But these are increasingly large concentric circles. And the problem is they're not even concentric circles. They're spheres. So if you imagine the amount of energy, had this been a cable, and you sent the energy down the cable to this receiver, most of your energy might be still in the cable there, but take that same amount of energy, and now you've got to go in every direction possible to all points on a sphere that you're trying to draw, like a bubble. And so there's a tiny, how many different dots are there on a sphere? Can you draw a million, a billion? How big is the antenna? Maybe let's just make it, how many antennas would you be able to lay out if you started pasting them onto the surface of a sphere? Let's say it's 1,000. So there's going to be 1/1000th of the signal strength here that would have arrived, and 1/1000, and that's only when it's close. Then you still have propagation delay, which is the square of the distance. So the strength of the signal here is really, really weak. It's almost nothing. And arriving at the same time at this receiver, at this radio at the other end, is all the garbage noise that everyone else is generating with the same frequency. We're all using the same frequencies. And sometimes other things are generating noise on here that aren't even supposed to be using it. Here's another problem. If that's not hard enough, a copy of your signal, you can draw a line that pierces all of these bubbles and makes its way all the way to the end. It's very, very weak. And if you're very quiet and listen very carefully, maybe you can pick up what the user is trying to send. But there's also a copy of it. I'm going to draw it right here, that bounces off this shiny glass on the front of this office building and also arrives, and it got there just an instant later. At the speed of radio, speed of light, it had to go a little bit of a greater distance. It had to go a squared plus b squared to your c squared. So if you figure out what a and b are. So I had to go a little further. And oh, by the way, a copy went here, and one bounced off of this, and up here, and on this floor, and down over here, and one bounced off the side of a car that's moving, and so 1 minute it's here, and the next minute it's there, and so your bits are actually coming in closer together than they should, because as the car moves, the angle changes, and you send the bits at a constant rate, but so you've got all that going on. So what really arrives here can be thousands of copies, at least hundreds of discernible copies of your signal, but they don't all arrive at exactly the same time, so they're interfering with each other. And yet we still have the ability to build the electronics to pick this off. One of the tricks for making this happen is something called MIMO, massively parallel arrays of antennas, basically. And what you'll find with technologies like 5G is inside this radio, they'll be pasted all the way around the inside of this radio equipment will be hundreds, if not thousands of antennas, all listening for exactly the same signal from you. And that feature, as well as putting lots of transmitter radios inside and transmitter antennas inside your radio, dramatically improves the ability to receive weak signals and do so error-free. I don't totally understand why. I need a double E to sit down and kind of try to explain, because it takes too much time for me to pull out a textbook and read on this as well. It's a little far afield, but it's interesting. So some of the 5G trials are showing by implementing even this antenna idea, they're able to get lots more users and lots more bandwidth out of a network. So that's one of the tricks that 5G is playing to make this stuff work for you. Okay, so let's plow ahead. We have a little bit of time, so I want to get us continuing on into the next lecture. And I'm not positive you have the slides for this, so let me crank these out real quick. Better be super quick. Oh, I already have the slides cranked out. Well, let me just drag them over then. Did I have the right one? They're the right ones. Okay, so I haven't changed this one yet. All right, so let's cancel out of this. So get back up to the top of this guy here and continue on with the next section. So looking back again at the devices, what this diagram implies is there are some special areas of the internet where there's only routers talking to each other with none of these end links, none of these hosts at the end. And for the purposes of teaching, that's a perfectly fine model, that there are some high-speed backbone providers that do not concern themselves with being ISPs and not connecting to access networks, and instead trading lots of traffic. But there are some users that they will let connect, big companies, for example, or important users, as well as their own administrators. So these are what generically we refer to as things that move those packets that we were talking about from one link that comes to the router out another link that comes to the router. This shows far too many of these little communication links. It would be like a spaghetti bowl, but the idea is accurate. So we call these packet switches again, but everyone calls them routers, and they are taking care of moving things around. If ever they come to a link that can't handle, for whatever reason, a packet of a certain size, they're certainly able to break your packet up into pieces, smaller ones, so they can get there. Sort of like if I send you to with a big box of food to the airport to take home after Thanksgiving break or after the holidays, and you get to the airport and they go, it's too big, it's going to cost you a bunch of extra money to do it, and you decide to break it into 2 boxes because you're there really early and do it, that's an example of fragmenting a packet apart, and you'll put it back together at the other end. So here's a diagram or an example of something with several switches. I've talked about most of this already. We've got all of our bits. You have to wait for them to drain out of this packet container and onto the wire and make their way across. But what we've added this time is another device in the middle. We've added a router in the middle. And so we have to wait for these bits to arrive at the router so that we can take a look at the packet, make sure that we're happy that it's intact, not corrupted. Whatever error checking bits that we've added in there, kind of as a numerical code, they're all still there as well, and that we're ready to continue transmitting things on to the next link. So having to wait for the whole thing to arrive and then forward it along is called a store and forward network. They've been around for centuries. It's the way the Postal Service works. You wait for the whole envelope to get there before you send it on. Well, you may not have realized there was a choice. Like, could they have shredded it and send it to me in bits and pieces? I don't know. I'm convinced they've done that to some of my mail before. But the reason why we still talk about getting the whole thing there is because when we're talking about packets, it's absolutely possible to send things a bit at a time. I get one bit from that user, and without waiting, I immediately forward that bit on. I get the next bit, I forward it along. I don't care what it is. I don't ever try to make sense of it. I don't try to put it together back as a packet again. If I'm the only one using the network, that's fine. That's the way a digital telephone call is transmitted. Don't need to wait for anyone. Bit by bit as it shows up, we can send those things just right along. But when it's a shared network, which is what this scheme was built to enable, then I need to keep things in packets to keep them organized, separated from each other, and identifiable uniquely. So here's a one-hop example. This passing through the router is a hop. And if it's got a packet to send that's 7.5 million bits, and the transmission speed is 1.5 million bits, then it's going to take 5 seconds of delay for it to sort of pour into this network and be all there so that it can begin its journey, back out again. So we only count the transmission delay either as you leave or as you enter, but not both. And that's generally the right way to do it, unless we're trying to look at specifically some unique way of counting things. So in that case, I have one delay of transmission when I send this thing, and I have another delay of transmission if I were to resend it again on the other. What this math is trying to convince you of for the moment is you actually have to wait for it to send and wait for it to arrive. But remember, we saw examples of this a minute ago. It's entirely possible that bits are already filling this thing up before you even finish sending. So it's not really fair to say you have to wait one entire transmission delay for this, and then once that's over, you start counting from 0 again, another transmission delay to receive it. It's not usually going to be that way. If it's a short network like this one is, there's basically 0 extra time to do it because this takes almost no time whatsoever. And an instant after you send the last bit, it's already across the network and immediately here. So you really only had to wait for this transmission to happen once because the second one was happening in parallel as this one. So, the end-to-end delay, they sort of with the diagram imply that it's here and here. What's really accurate to say in the way we really count it is there's one transmission delay leaving here, and there's another transmission delay which they did not draw leaving here. Right? So you count either the leaving or the resetting. All right. So got a chat question. So let me go see what that is. Is there such a thing as router? Oh, you better believe it. Wireless router security is web, WAP, WAP2, et cetera, PAPE, things like that. But there's also heavy-duty router security between routers with sometimes physical path separation and some things like that. You sometimes in these data centers they will insist that the cables from the phone company arrive over an engineered route where they walk with the phone engineer and they pick the street that they want it to go down, and they talk about what's in each manhole along the way, and they want locked manholes instead of just manholes that anyone can lift, and they want the cable to run in a concrete duct, which means you first install this concrete thing. It looks like a continuous brick with a hole down the middle, and then you run the cable. Some places you just have to lay the cable and then pour concrete over it, like near a bridge or something maybe, and then they'll want it to enter their building. Once it hits their property and it's their job, they don't want you just trenching it through the grass like they do for you and me. They'll want you to run it through steel or concrete there as well. That's if they really don't want anybody to be able to tap into it. And if you think that's good enough, you're good for you. You can keep that fantasy. I can point to examples of where if you really want to know what's going on, you'll dig underneath and come up through the bottom, bore quietly through the concrete, and tap into it that way without anybody knowing. So if you're going to do that type of security, you also need surveillance. You need to look for air pressure differences, temperature differences, vibration, sound, all of that kind of stuff. We burrowed. I had an uncle who, God rest his soul, he was part of a predecessor to the CIA, and was part of a team that bored underneath Hitler's bunker in Berlin to try to find out what they were doing and what was going on. There's an article that was released not too long ago where the United States for 15, 20 years had tapped into the undersea cables that the Russians used to communicate with their submarine bases around the world. And we knew everything for years and years that they were sending to their submarines. They might come out with an article like that of their own. You never know. So security is a whole world. For routers, there's absolutely security. Some of the most important security you can have in a router is to be very careful who you accept a change from that will cause you to route packets going to a certain network differently, called routing updates or routing rules. You have to be very picky about who you get rules from, and usually you will ship the router with hard-coded in the only place that they can listen for updates from. So everybody else can try tricking it into sending me copies of the things, and it won't do it. So that's some of the most important. So in this packing switching example, we show a blend of blue and red packets coming from computers A and B, and sometimes the network's underutilized and there's space. Sometimes the packets have to wait their turn because there's too many arriving at a time. And if you go back to the simulators that I was talking about, there's, oh, not, yep, this one. There's one for that as well. So let's say we start off with somebody that's sending me packets into my router, and that's what this ugly collection of rectangles is in the middle. This is my transmission wire. Packets are arriving 500 packets a second, and they're leaving 1,000 packets a second. It's never going to fill my buffer, never going to have an issue, no packets dropped. It'll keep count here for a long time. But what happens if I can send packets much less quickly than I'm receiving them? Well, you can guess what's going to happen. They don't arrive in an exact even distribution. There's a Poisson distribution that could be used to model the likelihood of the delay that between packets. So these things will fill and empty, but it's not like on a regular, like fill, empty, fill, fill, empty, fill, empty, fill. So, they're not empty, fill, empty, fill. It's not like soldiers marching in a parade or something. And it'll eventually get full, and it'll eventually drop packets. And when you run the simulation, it'll be different for you than it will be for everyone else in the class, because this thing is randomly generating intervals and sources and transmission queues and all of that. And so we sent 30 packets, and we dropped our first one out of 31 packets. So that's easy. My question for you is, what's going to happen if they match? What's going to happen if the sending rate, the Gazzetta rate, matches the Gazzetta rate, as I've heard some people say that I used to work with? So we'll leave that for something to figure out a little bit later. Okay, two key functions that are happening. The router is actually taking care of taking a packet and then figuring out where it needs to go and then putting it in that queue and getting it out the door. So removing it from one queue and getting it across the fabric. There's lots of connections on a router. Everyone's trying to move things across this central hallway from the input ports to the output ports. So there's contention and congestion. So you have to have really fast runners that can get that stuff doing. And that's switching fabric in the middle. And so that's the actual act of forwarding the things along. And then routing is the task of determining what decisions you want to teach the router how to make. So do you want to teach the router that if it gets a packet on port number 2 for port number 8, or rather from this network, it arrives on port 2 and it's trying to get to that network, send it to port 8, because that's the shortest way there. Or maybe later I'll change my mind and say port 6 as I update my routing table. So this is software that's running, trying to figure out how to make the best decision. And the product of that program is this table. And this table gets loaded into all of the cards inside the router. It's very fast memory, sort of a solid state affair. There's no disk drive. There's no time to go to software for any of this. Running any of this in software is old school. You don't have the time to do it. So you will run this in software, but the routing table that results you'll push down into basically a solid state drive, into super fast memory. All right, so those are two key functions. And what we've seen changing in the industry is this stuff still has to happen sort of in the router, the actual moving the packet. That can't be done somewhere else. But why can't this? I mean, this is just running a program to look at a bunch of data and make some decisions. And there's some reason that we really want to do this. No router has a map of the internet, and no router really knows the best path to send packets to all the places you go. Now, if it's a router at home, yeah, it's pretty obvious you only have one place, to the ISP. But I'm talking about more in the core. And it's a profound problem. We don't know where to send stuff. We make a good guess. It's a best efforts function, but it's, we want it to be better than that. So there's an analogy here. You're going to drive from the University of Houston to the campus in Victoria to, let's say you're driving over to Houston Baptist University. I'm picking something that I know if it's on the other side of town. It's going to take a while, and you don't like freeways very much, so you're going to take street level roads, and you'll start asking policemen at every intersection, what's the right way to go? They may not know everything that's happening on the route. They just know what's happening around them. And they'll give you a good decision based on that. And we can build math models that show that'll get you there. That should get you there as long as they're continuing to exchange information with each other in little regions and there's overlap. That's good enough. It may not be the best route. So if you're late and you're in a hurry, you're going to pull out Waze because Waze now, for the first time, gives you complete knowledge, an omnipotent being that rides above all else and can see everything to go. And they may tell you to go a direction that you think is just dead wrong leaving campus, but it turns out it's right because there's a bad accident that makes that other direction a bad one. So there's a way to export all the data collection that you and everybody else running Waze is doing all over the city. It gets pushed to a data center, a cloud, let's say in California for grins, and software there that's got plenty of capacity, way more than your phone, can analyze and push the route that you should do back down to your phone. So why can't we do that with routers? Why can't we take all that data, push it into the cloud, and let massive programs make truly perfect decisions based on all data available of exactly what the right routes are and just update it as we need to. So there's a huge move to try to get that done. And the company that's done most of this is AT&T. They didn't design it. They've implemented it, but they've done a lot of innovative work. They're miles ahead of everyone else. They've written textbooks on it, like college textbooks. They sent people to teach courses, particularly at UT Dallas, which is where AT&T is headquartered. And I know most of the people that wrote the chapters. I used to work with these guys, so they've just done amazing stuff. It's been a long time since I worked with them. I'd love to sit down and talk to them again and ask how it's been. And it's revolutionized the services they're able to offer customers. Okay, a few other things to kind of tidy up here, and we're doing okay. We maybe have a few things still to tidy up next time. So one of the things that we talked about was circuit switching, sending bits at a time, no packets, things flow through end to end like it was one big giant long cable, right? And telephone calls like that, television broadcasts like that, radio shows like doing that. Everyone, gets the same signal, so just send one continuous stream out. Why not? But we know that we can also stream those types of things over the internet. And the internet only does packet switching. So there must be a way to marry these two things up. And you can. If you have enough tools and enough luck, in place of if you don't have the tools, you can make the internet behave like a circuit switch network enough to satisfy the requirements of the user. So an example of that would be streaming KUHF over the phone with the KUHF app, the University of Houston's NPR affiliate. And it doesn't work perfectly. In fact, I would not say it works great. It pauses frequently. But I'm not really concerned about the delay so much because I'm not having a conversation with someone else. And what they basically are doing to get around the congestion that happens, which is what's causing the delay, is they break the packets up into very, very small ones. And they have a much better chance of surviving and finding space. If you show up at a router and you're small and the router's running out of memory, there's more chance that a small thing's got room to fit than a big thing. So just think about, a traffic jam. If you're on a motorcycle, you can weave between the cars and still there's enough room for you to make progress even though the truck's going to be stuck there for a long time. So the internet will accept this traffic, but it doesn't treat it any differently. It has to fight for its own. It commonly has issues, but if it gets there, then great. It's free. You didn't have to make a phone call or have another network. So if frequency goes up and time goes to the right, then what then is the difference between sending things one way or the other? Well, if we are doing true circuit switching, there are a couple of ways of doing it. One way to do it is to combine 4 users on a network like you see here. Each one gets a separate frequency. This is like 4 different radio stations. They're all available on your radio, but you get the same constant amount of bandwidth forever. That's okay if you're a radio because you always send exactly the same amount of data. You're just sending, an audio signal, and it's encoded a certain way, but it never changes. So you're never going to need to burst up. If you scream, it still needs the same bandwidth. If you whisper, It still uses the same bandwidth. So it's appropriate for that. The problem with this for the internet is we don't use bandwidth this way. We send a little bit and then burst up and we need to send a lot. So, we're sitting along here idle in this fuchsia bar at the bottom, fuchsia colored bar, and sometimes we want to burst up and use more bandwidth, and we can't. We're like locked into this slot. And if you want a scheme where you can use all of it occasionally, and in return, when you're not using yours, you'll let somebody else have it. That's the way we want the internet to work. So there's another way of doing this, which is time division multiplexing. And what that basically does is gives you the whole network, but only every so often. So this is the way the telephone network sends voice calls. I can pack a bunch of voice calls onto a circuit, and I send your bits, my bits, your bits, my bits, your bits, and alternating back and forth. But it still has the same problem for people trying to use this for data unless we have some scheme of combining these time slots or these frequencies together. So neither of these work, but that's what we kind of have to try to emulate on the internet if we want to give someone the illusion of packet switch networks. So Skype calls are like the bottom one, and streaming audio or Netflix or something is like the top one. So that's how we kind of get that stuff across. So why do packet switching then? Why not use circuit switching? Well, let's look at a circuit switched application. We can beat circuit switching at its own game. If we have a 1 megabit per second link and each user, when they're talking, uses 100 kilobits per second or a tenth of the network, and they're active only 10% of the time, on a circuit switch network, I can only fit 10 users on that. Right? So even when each of those users is idle and not doing anything, I'm kind of locked into this scheme where nobody else can use it. So I can only have 10 people on it at a time. But with packet switching, if you do a little bit of the math behind it, if you are willing to mess up and drop someone 0.0004 or 0.04% of the time, then you can fit 35 users on that same bandwidth that circuit switching could only fit 10. And you can get the same thing done. So I'm going to copy this. It's another one of these simulators. And we're going to copy over here. And I don't really remember this one. So here we go. It's this first link here. So what this will basically do is walk you through one of these examples, ask you questions about it, and then you can show the solution at the bottom, and it will explain exactly how they did it. Then you can say another problem like this, and it will randomly mix up all the numbers and do the same thing again, and then you can randomly solve it and pick the answers at the bottom. So I'm going to give you a homework like this, and no two people will have the same problem because I'm going to ask you to generate your own. All right, so that's a second type of problem. It's not just an animation. This one is actually to solve problems. So you should be able to master that math after going through that a few times. Okay, to wrap kind of this up here, is it a slam dunk winner? Well, it's great for bursty data. It's simple. There's no call setup, meaning you don't have to do all the addressing and set up all the things up front. You just let loose a packet and let the network figure out as the packet goes along. Oh, I just saw a packet that needs to go here. Where should I send it? You'll let them figure it out as they go. You can have congestion, and you need some more tools than we give you on the internet today to really make this thing act like a true circuit switch network. So back to the internet for one last kind of quick look here. It's a collection of networks. It's a collection of ISPs. And so if you are one of the ISPs on here, you may want to have a connection to everyone else, but that's crazy because then everybody want to do that, and pretty soon you have an order n squared number of connections. So that's not what we do. What we do is build a hierarchy of these things and have some providers in the middle, getting back to the beginning of the lecture, that picture I showed you. In fact, what we can have are people that are regionally responsible and then overlay them with connections that get them talking to each other, and maybe have some special types of locations that float up above that we can use to poke holes in everybody's networks and let traffic drain out over to me. So this would be like Equinix, for example, a place where you let everybody kind of exchange traffic. So some of these access networks can get in here, some of the ISPs can, some of the global ones can, some of the big service providers like Netflix or Amazon Web Services can get in here as well. Most people that have popular hosted programs, Dropbox would be in every one of these things, for example, to exchange traffic because it reduces the amount of time you spend taking the long way around the internet, which is good for everyone. There's sometimes regional networks. We have those in Texas as well. And then we don't have time to talk about this today, but we need to spend some good quality time talking about content provider networks. They'll come up again in the class, but they're becoming super dominant. I want you guys to have a really good handle on what's going on. So a peering link is, I'm really glad you spell check. I was just going to let that go. I thought maybe I had said something. I'm poking holes, and sometimes I slip and say a word I don't even hear myself say it. So a peering link is where you have peers, your peers, somebody who's at the same level as you, and you exchange traffic directly with them. So you can have peering policies. If you hand me traffic from ISP A and I'm ISP C, I will take it as long as you're not trying to use me as a shortcut to get to B. You should have your own peering connection with B directly. So I will take traffic from you to get to all of my other networks downstream, and I expect you to take traffic from me to get to all of the ones that you connect to downstream, but don't ask me to haul traffic that's not even for one of my customers. Right, so that's kind of what peering is. Okay, guys, got to run. I will see you soon back in class in person on Monday, and I'll send out a homework. Have a great weekend. Remember, watch for the email. No email, no homework. Bye, guys.